recently we have been talking about LTI capacitor and LTI inductor, deriving their properties and gaining some familiarity with some simple topologies, some simple circuits that contain those components. Okay. Now we have reached the point where we're now sort of ready to start developing tools that allow us to analyze dynamical circuits in general. Okay. So we will begin considering first-order circuits, first-order dynamic circuits, which roughly means a circuit, an LTI, well, we're going to consider the LTI case, which means an LTI circuit that contains a single dynamic component, either an LTI capacitor or an LTI inductor. Once we thoroughly study first-order circuits, then we will move on to the second-order circuits and finish the course. Okay. And the next course, in the follow-up course, 202, we will begin with dealing the nth order, or the circuits of the general case. Okay, but now let's develop a solid understanding of first order circuits and then second order circuits. Okay. Now we begin with the simplest case, that is where the circuit does not have any external inputs. Okay. So that is called, or the response from such circuit is called the zero input response. Okay. So this means response or solution of a circuit to initial conditions only. Note that for an LTI resistance circuit, if you have no input in the circuit, then there's nothing to solve. Everything is zero, every voltage and every current. However, with dynamic circuits, that's not the case. Even if the inputs are, the external inputs are zero, that is, the voltages from independent voltage sources or the currents from independent current sources, even when they're all zero, still we have something non-zero, still we have some meaningful or interesting response, and the reason for that is the initial stored energies contained in our dynamic components, okay, the capacitor or the inductor. Now we're going to study that, how the initial voltage in a capacitor or an initial current of an inductor gives rise to the response, and that response is called the zero input response. Okay, so let's consider the simple case. We have a capacitor that's connected in parallel or series, depending on how we look at it, with an LTI resistor. Okay, the capacitance is C, resistance R, and the initial voltage of the capacitor due to the initial stored charge in the capacitor is something, okay, and that something we denote by V0. Okay, so let's do some labeling. This is VC, this is IC, this is the resistor current. Let's call this voltage VR. Okay, well, clearly VC and VR, they are the same, and IC plus IR is zero due to KCL. Okay. So the question is, what's the capacitor voltage, ECT, for all future times? Okay, we start from the initial time, t equals 0. Now, we're going to introduce a notation that simplifies analysis a little bit, and that's the capital D notation. Okay, when we write df, f is a function of time. What we mean is d over dt, f of t, that is the time derivative of the function f. Sometimes we also use the dot notation, okay? F that means the same thing. Okay. So, to figure out VCT, first we have to figure out the equation that should be satisfied by VCT, and that equation will be a differential equation, and that differential equation will be a first order differential equation because the circuit contains only one dynamic component. To obtain that equation, we start from the terminal equation of the capacitor, which is the current is proportional to rate of change of voltage, okay, and the proportionality constant is capacitance. So from that we reach, okay, we can write the following: dVc equals 1 over C IC. Okay, so we put dVc, VC dot to the left hand side. Then what we want now is we want the right hand side also to be in terms of VC only. Okay. So for that we would use KCL, KVL, and the terminal equation for the LTI resistor. So by KCL, okay, IC is minus IR, so we have therefore this equals minus 1 over C IR. And then this equals, by the terminal equation of the LTI resistor, VR over R. And finally, by KVL, VR and VC, they are the same voltages, so we have minus 1 over RC VC. Okay. Now, it's usually convention that we collect all VC terms and its derivatives on the left hand side, and if you do that, this is what you have: dVc plus 1 over RC VC equals 0. Okay, so let's call this equation 1. So this is the equation, or this is, you can call it the constraint that capacitor voltage is subject to. Okay, so whatever VCT is, it must satisfy this differential equation. Now, equation one is a first order homogeneous. So first order, because the highest order term is this dVc term, okay, and it's the first order differentiation. Therefore, this equation is called the first order differential equation. And it's also called a homogeneous differential equation, and the reason is that the right hand side is 0. And by right hand side we mean when you collect all the VC terms, or for inductor IL terms, let's say, on the left hand side, and what remains is what we call the right hand side. In this case, nothing remains here, okay, because we have no input in the circuit. That's why we call it the zero input response. Homogeneous differential equation. Okay. Once again, the right hand side is 0 because we have no input in the circuit. Solution to this equation has the following form. VCT equals some constant, and then we have multiplied by an exponential. Okay, this is our EE201, EE201, and so on. Okay, so and T is time, and K and S, they are parameters, okay, constants to be determined. Where constants K and S are to be determined. Okay, so how we can determine those two unknowns? Okay, so two unknowns mean we need two equations. Here is one of our equations, okay? And how about the second equation that we require? And the second equation that we require is here, the initial condition constraint, okay? And Using both of those constraints, we will be able to figure out uniquely the solution, that is, uniquely the pair K and S. Okay, so let's do that. Okay, and what we're going to do now is this is our solution candidate. We'll put that candidate into the first constraint, this constraint, okay, into differential correlation constraint, and then we will also put it into the second constraint, and that will give us K and S. So d over dt, K e to the st. Okay. Now we're plugging this candidate into the differential equation. Plus 1 over RC equals 0. Okay. That yields K S e to the st plus 1 over RC K e to the st equals 0. And that can be written as S plus 1 over RC times K e to the st equals 0. Okay. And this implies, unless K is 0, that S has to be minus 1 over RC. Okay. And this is an important parameter describing the circuit, therefore it has a name. And the name is natural frequency. Of the circuit. And now, having determined S, let's also try to figure out K. So what we have obtained is VCT equals K e to the minus T over RC for T greater than or equal to 0. Okay. Note that no matter what K you pick, that function or that waveform will always satisfy the differential equation. Okay. So therefore we cannot gather any further information regarding, for instance, K from the differential equation. So we have to look elsewhere. Okay. To answer the question, how about the constant K? And that elsewhere is no other than the initial condition constraint. So let's remember that initial condition constraint is V0 equals the value of capacitor voltage at T equals 0. So this is something given. It's not something that we figure out. It's minus 6 volts plus 18 volts. It's something. Okay, so VC0 this is our VCT candidate. So K e to the minus T over RC, and then we evaluate this at T equals 0. If you plug in T equals 0, this becomes 1 times K is K. Therefore, K has to be the initial voltage of the capacitor. Therefore, K is V0. So K is determined. S is determined. Therefore, everything is now known regarding the capacitor voltage. Hence, we can write VCT, the solution of the capacitor voltage for all future times, T greater than or equal to 0, is initial capacitor voltage, and that's minus T multiplied by minus T over RC. Okay. So how that waveform looks like is as follows. T0 VC of T. Suppose that V0 is positive, and also suppose that we're dealing with a passive circuit, that is both R and C are positive constants. Therefore, here we have an exponential, and it's V to the minus something times T. Therefore, as time goes on, this becomes smaller and smaller, so it's decaying toward 0 exponentially. Okay. So what we have is something like this shape. And this is where we start, VC0, and that's the initial voltage. Okay. Let me put a remark here. This product, RC, sometimes noted by tau, is important clearly on the behavior of the solution, and therefore it has a name. It's called the time constant, okay, of the circuit. It's sometimes called the time constant. Now that smaller the time constant, okay, the faster the response. Okay, if it's very small, then this VCT becomes practically 0 in a very short amount of time. If, however, it's large, then it will be more sluggish, okay, to move toward 0. Okay, let's also quickly figure out the remaining signals in our circuit. VCT and VRT, they were the same due to KVL. Therefore, this is also the voltage appearing across the terms of the resistor. Okay. How about the currents? The capacitor current and the resistor current. Let's also figure them out. Okay, so how about the remaining variables ICT and IRT, capacitor current and the resistor current. Now, ICT, to figure out ICT, we can use the terminal equation because at this point we know what the capacitor voltage is. So ICT is C d over dt VCT, and we know what VCT is. It's here. So that's C d over dt E0 e to the minus T RC. Okay. One last thing about working with exponential functions is they're very easy to differentiate and also integrate. So that yields minus V0 over R e to the minus T RC. Okay, so that's ICT. How about IRT? Well, we know that by KCL it has to be minus ICT, but let's approach figuring out this current from a different point of view. Let's start with the terminal equation of the resistor, VRT over R. And what's VRT by KVL? It's VCT over R. VCT is, okay, here. Therefore, that equals V0 over R e to the minus TRC. Note that IC and IR, they have the same magnitude but opposite sign, which they must because of KCL. KCL, as expected. Okay. How about those waveforms? This is ICT. If, as we did here, we take V0 to the positive, then IC will be negative, and it will have a similar shape. With VCT, only it's upside down and scaled with 1 over R. Okay, so we start from minus V0 over R, and this current is decaying toward 0. And that immediately gives us the shape of IRT. The same thing here, only it's put upside down. This is easy over. Okay. Now let's also see a zero input response case with an inductor R, other dynamic component, and then we can move on to considering circuits with non-zero inputs. This time, instead of capacitor, we have, suppose, an inductor. L, R, VL, VR, IL, and here we have IR. And for this circuit, let's try to figure out ILT for future times, t greater than 0, given the initial condition I0, okay, some constant. Okay, so as before, that is, as for the case with the capacitor, we start from the differential equation or the terminal equation for the inductor, and then what we want is we want to obtain an equation only in terms of IL and its derivative. Okay, so DIL equals 1 over L VL. Okay, so that's the terminal equation for the inductor. Now what's VL? VL is VR. 1 over L VR. Okay, and VR is R by R, and IR is by KCL minus IL. Minus therefore, the differential equation is DIL plus R over L IL equals 0. Again, we have 0 on the right-hand side because this is an input-free circuit. Now, the natural frequency for this case is S equals minus R over L. With capacitor, with the previous circuit, it was minus 1 over RC. Okay. And that yields ILT equals some constant to be determined by the initial condition, and then the natural frequency times T. Minus R over L T. And the question is, what's K? Now K in the case with capacitor was determined by the initial condition. Here we're gonna use the same constraint to figure out K. Okay, so this is a solution candidate. No matter what K you pick, it will always satisfy the differential equation. So you have to look elsewhere to figure out the exact value of the K, and where you have to look at is the initial condition. Okay, so evaluate this at T equals 0, and it must equal I0, and that immediately gives us the answer for K. K equals I0. Initial condition constraint. IL0 must be I0. That says K must be I0. Hence, we have obtained the solution for ILT. Therefore, ILT equals I0 e to the minus R over L. Okay. circuit, what's the time constant? Okay, so we put it here sometimes. We write this instead of ILT equals I0 e to the minus t over the time constant. The time constant for the capacitive circuit was RC, and now it's L over R. Okay, where L over R is the time constant. And smaller the time constant, faster the response. Okay, now we're ready to start talking about circuits, dynamic first order circuits in the presence of non-zero inputs. Okay. So that we will study. Well, first we will study the simple case. Okay, non-zero input and the initial conditions are 0, and then we're going to consider the general case, that is both the inputs and the initial conditions are allowed to be non-zero. So zero state. Okay, so by definition, it means response of a circuit with zero initial conditions. Let's consider the following example. In this example, we're going to consider the simplest possible input, that is a constant input. Okay. Constant. This is the circuit. We have a constant current provided by an independent current source. And here we have a switch to isolate this input from the rest of the circuit for negative times. And this switch will be opened at the initial time t equals 0. And then the remaining of the circuit is a capacitor and an LTI resistor. Okay. So C R, this is IC, this is IR, and this here is capacitor voltage, also the voltage of resistor and the source. The source here provides constant current at I. Okay. Now this switch is initially shut. Therefore, here we have a short circuit, meaning that this voltage is 0. And that means that initially there is no charge on the capacitor. Okay. And then we open the switch at t equals 0. Once the switch is open by KCL, the sum of these currents are forced to be I. Okay. And due to current coming from here, the capacitor will start charging. Charging means its voltage will move away from 0, and now we're going to figure out how that motion occurs. Okay. But first, note that the initial capacitor voltage VC0 minus just before the switch is open equals 0. That's why we can say that this is a circuit with 0 initial conditions. And hence, what we're dealing with here is zero state response. Matches that definition. Okay, so what we're going to do now is, well, we have to figure out the capacitor voltage, and for that, again, we're going to use the we have to obtain an equation, a differential equation, that describes the evolution of the capacitor voltage. And for that, what we do is we start from the determinant equation for the capacitor. Okay. Then we will obtain the differential equation that we are. Okay. Now for T positive, that is after the switch is open, we can write the following. Okay. dVc equals 1 over C IC. Well, we can write that for all times. Okay. But for some of the things that we're going to write afterwards are valid only for T greater than 0. So we start with the terminal equation of the capacitor. Okay. That equals 1 over C. Let's rewrite IC in terms of other things. Now, the switch is open. Therefore, by KCL, this constant current I equals IC plus IR. Therefore, IC is I minus IR. Minus IR. Okay. And that equals 1 over C I. Now, that we want everything in terms of the input and the capacitor voltage, our formulation area. Now, IR is VR over R, and VR is no other than VC. Therefore, we can replace this IR with VC over R. Okay. And that's what we want. Everything is in terms of our formulation variable, capacitor voltage, and the terms coming from the input. In this case, I. So let's reorganize the equation by which we put all the terms of VC and its derivatives on the left-hand side, and the remaining terms, keep the remaining terms on the right-hand side. If you do that, this is what we have: dVc plus 1 over RC VC equals I over C. Okay. Now, this non-zero right-hand side is what we can call the input term. Okay, now the question is how to obtain VC. Again, we have two constraints. One of the constraints is the differential equation constraint, and the other constraint is the initial condition constraint. This time, initial condition is 0. Now, this is how we approach when we have a non-zero right-hand side, when we have an input. Solution is of the form we say VCT equals VHT, this we call the homogeneous part of the solution, plus VPT, and that we call the particular part of the solution, the particular solution. So this is VHT is homogeneous solution. And VPT is what we call the particular solution. Okay? What we're going to do, we're going to figure out the homogeneous solution, we're going to figure out the particular solution, and by summing them up, we obtain our overall solution. Okay, so let's do that. Find the homogeneous solution. What we do is we ignore the right-hand side. In the differential equation, okay? By ignoring, we mean we replace it by 0. And then once you do that, you obtain a homogeneous differential equation, and that's why we're calling this piece the homogeneous solution. Then we have dVc plus 1 over RC VC equals 0. Instead of the actual right-hand side, now we're considering 0 here. And we already dealt with this situation. We know how the solution, or the form of the solution, is for this homogeneous differential equation. And that's VHT equals K e to the minus T over RC. Okay. And for the zero input case, we determined this K using the initial condition voltage. Okay. But this time, we just let K be. Okay. This one we don't touch now. So that's our homogeneous solution, and for any K, clearly, it satisfies this homogeneous differential equation. This is homogeneous solution, and K is to be determined later. Okay. And this tells us the natural frequency of the circuit. It's minus 1 over RC. Okay. And here is something that's important. The natural frequency of the circuit does not depend on the input. Okay, so because it's determined by the homogeneous part, the homogeneous differential equation. Okay. So this is a general statement. It's true for any ordered circuit. If you have an arbitrary dynamic circuit, LTI dynamic circuit, you can kill all the sources within that circuit and obtain the differential equation describing, let's say, some variable, capacitor voltage or inductor current. And then the natural frequencies coming from that equation are the natural frequencies of the circuit. Okay. And this natural frequency, by definition, time constant is RC. Now, to find the particle solution, what we follow is the following algorithm. VP has the same form, okay? So we will, at this point, let's not be precise about what we mean by form, but in this case, it means that input is constant, therefore the particle solution will also be constant. As an example, input constant, therefore we're searching for a constant particular solution candidate. Okay. Hence, let's VPT our particular solution candidate to be some constant which we denote by A. Okay, and then we're going to determine that A now. Okay, how we determine A is this particle solution candidate. We directly put it into the differential equation that describes the capacitor voltage. Okay, and that immediately will give us the particular solution. Now substitute your particular solution candidate, VPT, in the differential equation. That describes the evolution of the capacitor voltage, or whatever your formulation variable is. So the differential equation was dVc plus 1 over RC equals I over C. Okay, and now instead of Vc we have the particular part of the solution, so we put Vp, and now what we're going to do is we're going to let Vp be our candidate, which is a constant. Okay. So Vpt equals a constant. And the particle solution must satisfy the differential equation, and that will immediately give us what A should be. So let's do that. If you plug in this constant into differential equation, what you have is d over dt, constant. You're taking derivative of constant, therefore this term goes away. Okay. And what you're left with is 1 over RC times A equals I over C. And that yields A equals I times R. A over RC equals I over C. Therefore, A must be I times R. Hence, the particular solution is this constant I R. Okay, at this point, the particle solution is known because I is known and the resistance is known. Now, we have the particle solution that's determined completely, and we have the homogeneous solution that's partially determined. Okay, we don't know yet what this K is. Now, to figure out that K is, what we do is we combine homogeneous and particle solution. We sum them up to obtain VCT, the overall solution. And at that very last step, we subject that overall solution to the initial condition constraint, which in this case is 0. And that will give us what K should be. Hence, the overall solution is VCT equals VHT plus VPT, homogeneous solution plus particular solution. And that is K equal minus T over RC plus IR. At this point, K is unknown. Okay, to find K, we use something that we haven't used so far, that is initial condition constraint. Use the initial condition constraint. K equal minus T over RC plus IR, evaluated at T equals 0, must be 0. Okay. And that immediately gives us K, because at T equals 0, this exponential term is 1, so what we have is K plus IR equals 0, meaning K must be minus IR. Okay. Now everything is determined. Okay, so finally, VC2, VCT has to be IR1 minus E to D minus T over RC. Okay, so this is the zero state response to the constant input for our circuit. How it looks like is the following. Suppose that I is positive 0, so we start from 0, so that's our initial condition. And as time goes on, okay, initially this is 1, so 1 minus 1 is 0, so we see 0 is 0. Then as time goes on, this becomes smaller and smaller exponentially, therefore this becomes closer and closer to 1. Okay, it starts from 0 and it's going to 1, therefore VCT must be approaching IR in the limit. Okay, so therefore we're expecting shape